In this video, we are going to study the last idea of the promise semantics, which is promises. Uh, is one of the key ideas of these promises semantics. So the name of the semantics is named in such a way. So it is promises semantics because it supports promises basically. So the promise is basically trying to model store hoisting. Store hoisting means that a later store may be reordered across an earlier instruction so that the later store may be executed beforehand. So it is in the field of the concurrent programming, it is known as a major open problem for programming language semantics of the concurrency because of the following reasons. So it is not it doesn't seem very difficult at first, but it is actually a little bit difficult for the following reasons. So let me first explain what is store hoisting. So this example is, as we discussed in the previous videos, the store hoisting. The left thread is reading from X and then writing the read value to Y. And thus, in the second thread, Y is read and then X is written 1. The question is it possible to observe R1 equals R2 equals 1 at the same time? It should be possible because in the left thread, the X equals 1 store may be reordered across the first read, because they are accessing different locations. So the compiler may reorder those two instructions, or architecture may reorder those two instructions as well. If it happens, if they are reordered, the store hoisting behavior is observable because X may be stored first, and then X is read here, and then Y is written 1, and then the written value 1 is read here. So by just reordering these two instructions, sequential consistency or interleaving semantics exhibit the behavior in question, namely R1 equals R2 equals 1. So it should be possible. Then now let us see a little bit different program than the previous one. Now this is the same program except that the store instruction here is X equals R2 instead of X equals 1. So effectively, the left thread is copying the value of X to Y, and the right thread is copying the value of Y to X. Then in this example, the behavior, the same behavior, R1 equals R2 equals 1, should be forbidden because the value 1 is just out of thin air. They are copying values, and from the initial state where all the values are 0, all the value you can get should be 0 because only they are copied. 1 is just popping from thin air. So that's the reason why this behavior is called out of thin air behavior, and also this behavior should be forbidden in any possible semantics. So it is not only strange, but it also breaks all the reasoning principles that we will learn in the remaining of this course. So if you allow this behavior, then you really cannot program you really cannot use synchronization patterns in concurrent programming. This should really be forbidden. What is complicated a little more about this problem is that, okay, you may see that the differences between the two examples is that the first example has no dependency between the two instructions in the right thread. And the second example has a strong dependency between the two instructions. So you may say that, allow the first behavior by reordering the two instructions, allowing reordering of the two instructions because they are independent with each other. And we can disallow the reordering of the second example because there is a strong dependency between the two instructions. However, it is not that simple because of the third example here. So in the third example, y is read first, and then depending on the read value, if it is 1, x equals r2 is executed, and otherwise x equals 1 is executed. So basically this is a mixture of the two examples above. The left thread is the same as usual, and the right thread, the first instruction is the same, but the second instruction is mixed. If R1 is 1, then it is going to use the instruction from the second example, x equals R2, and if it is 0 or other values, then the first example's instruction is executed, which is x equals 1. So the behavior in question, R1 equals R2 equals 2, in order to get this behavior, you should take the branch. So R2 should be 1 and x equals R2 should be executed. So you may guess that, oh, this instruction should be forbidden because the instruction that is executed is the same with the instruction that is executed in the second example. So the second and third instruction execute the same instructions, so we should not allow this behavior as well. So it is a plausible argument. Another reason is that there is a dependency between the two instructions. So reading from y has a dependency on the writing to x. So first, there is a control dependency. So the condition is using R2. So depending on the value of R2, this instruction may be executed or not. Second, the data, there is a data dependency. X equals x, y is read, and the read value R2 is assigned to x. So there is a dependency in two ways. One is control dependency here, and the data dependency here. But it is not the case. So in the real world, this should be allowed. On the contrary to what you may imagine from the similarity with the second example. So this else x equals 1 plays a key role here. So let me explain why this should be allowed in any plausible, any sane semantics for programming language concurrency. So first of all, compiler may forward R2 equals 1 in the then branch. The reason is that in the then branch, you may be absolutely sure that R2 should be 1 because R2 equals 1 branch is taken. So R2 is 1 in this branch. So as a result, you may replace R2 with 1. This is called a stall forwarding or constant propagation optimization in the compiler pipeline. So it is one of the most basic and the most widely used optimizations. So it is really impossible to turn off this optimization. So because everyone uses this optimization. So you have to take that this x equals R2 may be replaced by compiler or with x equals 1. Now, the then branch and else branch has the same instruction. This is replaced with x equals 1, and this has x equals 1. So x equals 1 is executed regardless of whether R2 is 1 or not. So what is happening here is that a compiler may hoist this x equals 1 out of this if then else statement. So regardless of r2 equals 1, x equals 1 can be put out of this branch. So r2, though it may be executed right after a reading from y before going into this read, if then else. And then if then else is can be removed because there was no instructions inside this if then else. So as a result, by this two-step transformation, we may get the first example here, executing x equals 1 and then do nothing. The third example may be transformed by the compiler to the first example, and as a result, the first behavior, this behavior in question, should be allowed. So let me summarize the situation here. The third example looks very suspicious. So it is almost the same. It looks like almost the same with the second example. So you may guess that this should be forbidden. However, there is a concrete example, concrete explanation why this should be allowed. The reason is that compilers perform optimizations, that is widely used optimizations. And the optimization may transform the third example into the first one, thereby allowing this behavior. And actually, this behavior is observable when you compile this program into, for example, x86, for example, ARM architectures or RISC-V architectures. So the challenge here is that we need to find a semantic model in this view semantics, where the first example and the third example is allowed, but the second example is disallowed. The key here is that allowing the third example here. How to allow this behavior even though there is a dependency between the first instruction and the store instruction. That is basically the key problem of this modeling store hosting in concurrency semantics. Okay, so let me explain the idea here. So how to allow the third example. So the key goal here is, as I said, allowing hosting of semantically independent writes. And so in this example, this is independent, this is dependent, this is syntactically dependent because there is a data and control dependency. But as you see, the compiler optimization may remove the dependencies, so there is no true a genuine dependency between this read and this write. So we need to find a way to decide whether there is a semantic dependency of like in example 1 and 3, or there is no semantic dependency as in the example 2. The idea is that semantically independent writes are always writable in the future. So regardless of the execution, there is a way to execute a future write. If it is possible, if it is the case, then the write is semantically independent from the current program counter. And as a result, we may hoist the always writable store for now because it is semantically independent. So let me see the example here. At this point of time, we want to store the store here. The store is here, but we want to execute the store at this point of time. But you can see that from the in this execution, so x equals 1 will be always executed, regardless of the value read from y. X equals 1 is always executed. However, in the second example, the x equals 1 is not always executable. If, for example, you read y equals 0, then you are going to write x equals 0. not x equals 1. So at this point of time, you cannot hoist the store because it is unclear whether you're going to store x equals 1 or not. In the third example, at this point of time, surprisingly, x equals 1 is always writable. So it's the reason. If y is reading 1, then you are going to then branch, then you are going to write x equals 1. Otherwise, you're going to go to else branch, then you are going to execute x equals 1. So regardless of the value read from y, you're anyway going to write x equals 1 in the future. So this is compatible with this notion here. X equals 1 is always writable in the future for the third example. In other words, x equals 1 is semantically independent, right? From the point of view at this point. When the program counter is here, x equals 1 is always writable. And as a result, this can be hoisted at this point. So at this point, x equals 1 may be executed by the semantics. So that's the key idea. So we need to allow such hoisting based on this notion of semantically independent rights. So how to do this? So as I said, the mechanism or idea here is that we allow speculatively write a thread to speculatively write a value. Or in other words, we are going to say a thread may promise to write. And the thread should always be able to write its promises in the future. For example, if it has promised to write x equals 1, it needs to be able to fulfill the promise by actually storing x equals 1. And this is the way of modeling hoisting. And as a result, if a thread has already promised to write a value, x equals 1, the other thread may read the value because the promised value is not only just a promise, but it is also an actual thing. It is a hoisted store, so the other thread may freely read from the hoisted value. So that is basically the mechanism. And this is the high-level mechanism, and let me explain how this idea can be applied to the above example more precisely. So this is the example, the first example, store hoisting without dependency. So let me explain why this should be allowed in the promising semantics here. So let's first promise to write x equals 1 from the second thread. So let's say that this block, which looks different from this normal block, it is a promised block. So let me say that thread 2 wants to promise to write x equals 1. So it is the only thing you can do to get this behavior, because if you read first, then you're going to get the value 0. So at this point in time, when you read the value, then the value should be 0. And as a result, you cannot get the behavior in question. So the only action that is enabled by the promising semantics is promising to write x equals 1 by the second thread. Okay, so far so good. But in order to promise to write the value, you need to make sure that at this point of time, you are going to be able to write x equals 1 in the future. So let me see why. So first, the second thread needs to be executed alone. So in other words, from the thread 2's point of view, thread 1 cannot do anything, cannot help B. to promise to write x equals 1. So the hoisting should be happened from my own information. That's the reason why I'm going to hide the thread 1. And in the thread 2's point of view, I need to be able to fulfill the promise by actually writing x equals 1. And we should also assume that there is an interference from the other threads by filling out the memory. The current memory is filled out by some other things, so that I cannot assume the behavior of the other threads. Other threads may arbitrarily interfere with the memory, so that I should be able to deal with such interferences. So under any circumstances, under any interferences, I need to be able to fulfill the promise by writing x equals 1. So now let's assume that this is the interferences, and you can read 0 from y, updating the view to not updating the view at all, because your view is already on the value 0, and then you can fulfill the promise by storing 1 to x. So that's the reason why this example is allowed. You can promise to write x equals 1 because you are going to be able to, you have an ability to fulfill the promise. You are able to write x equals 1 under any circumstances and under any interferences, and you alone. So thread 2 alone can fulfill the promise without any help from the thread 1, and under any circumstances or any interferences in the memory. So that's the reason why this promise is certified. That means that, from thread 2's point of view, x equals 1 can be executed before or hoisted in such a way that it can store to x before reading from y. And this certified write enables the thread 1 to read x equals 1. So from thread 1's point of view, it can read the value here, because the certified value is also a valid value, and the other thread can read this block. So x equals 1 is read here. It can be read here. And then it also enables the thread 1 to write y equals 1. And now it is the time for thread 1 to execute the behavior. So first, it may read y equals 1 because it is already written in the memory. And furthermore, it can finally fulfill the promise, the x equals 1. But beforehand, it needs to make sure that the action here, reading from y, the value 1, and can be certified again. Because I said that in any case, you need to be able to fulfill the promise. So when you execute thread 2, which has an ongoing promise, for each step, you need to recertify the fact that you're going to be able to fulfill the promise. So let me explain this point later. In any case, in every step, you need to verify you're going to be able to fulfill the promise. So at this point of time, it is also certified because you can just write x equals 1 here. So it is recertified in this step. And finally, you can actually fulfill the promise by writing x equals 1, finishing the execution. So if it is the execution, then the behavior in question, which is r1 equals r2 equals 1, is exhibited. So Moral of the story is that x equals 1 can be hoisted because there is no dependency between the first and the second instruction in the write thread. And this is semantically captured by the promises semantics because at the beginning of this execution, x equals 1 may be certified, promised, and certified, and as a result, effectively the store may be hoisted. So the effect is that the store is hoisted because x equals 1 is put in the memory for the first step, and the second thread, in the first thread may read x equals 1 and then write y equals 1. Then the second thread may read y equals 1 and then fulfill the promise and this all behaviors are used to justify the fact that x equals 1 can be hoisted, and that is represented as the fact that x equals 1 is promised at the beginning of this execution. Okay, so far so good. And this is the second example where the store hoisting should not happen because of the out of thin air behavior. X is copied to y in the left thread, and y is copied to x in the second thread. So the value 1 should not popping from the out of thin air for both R1 and R2. How to do this? So suppose that we want to promise the same value by the second thread, x equals 1. But in this case, it is not certified. The reason is that the second thread cannot execute it alone and write x equals 1 from the second thread, because the only value it can reliably read is y equals 1, y equals 0, and then x equals 1 cannot be executed because the only value it can write is 0, x equals 0. So this is not certified, and as a result, x equals 1 is not promised. In other words, x equals 1 cannot be hoisted across the earlier instruction. And that's the reason why the behavior in question cannot happen in this example, in this promising semantics. So let me explain the final example where there is a syntactic dependency, but there is no semantic true dependency between the first and the second instruction. So the story is almost the same for the first example. The second thread needs to promise to write x equals 1. And let me certify this execution. The second thread, it needs to fulfill the promise by writing x equals 1, and you need to make sure that you can actually do that alone without any help from the first thread, and under any circumstances and under any interferences that is represented in the memory as an additional non-deterministically added memory blocks. So you need to make sure that under any interferences in the memory, you need to be able to alone store x equals 1 in the future. So let me explain why. The second thread may read y equals 0, and as a result, you can go to the else branch, and then you can write x equals 1 in this branch. So the promise is actually fulfillable. You can later actually execute x equals 1 in this case. So x equals 1 is fulfilled. And you may note that this is certified thanks to this else branch, because at the beginning you should go to the else branch and then you can write x equals 1. So this is the reason why the second thread is able to promise to write x equals 1, the else branch. Now, the story is almost the same for the left thread. It is reading 1 from the promised value, and then it is writing y equals 1, finishing its execution. Now, story is the same for the first instruction. In the second thread, it may read y equals 1. And after reading y equals 1, as I said, we need to recertify the execution. So here, the execution is recertified, but with the different branch. So you already read y equals 1. So R2 should be 1. So in the certification, you need to go to the then branch and then execute x equals R2, which is 1. So x equals 1 is anyway executed. But the moral of the story is that in the initial certification, in the first certification, the else branch was taken. So x equals 1 is executed. But now, after reading y equals 1, then the recertification, the second certification, is going to execute the then branch. So x equals R2 is executed instead of is x equals 1. So it is very much different from the earlier example. The promise, the two certifications are taking different branches, different instructions basically, but with the same effect in the memory, x equals 1. So that's basically the reason why this mechanism of promises and certification captures the syntactic dependency and the difference between syntactic and semantic dependencies. So even though the instructions that are executed are different, which means there is a syntactic dependency, they are doing the same thing. So there is no semantic true dependency. So this mechanism captures the difference between them. And next, in the then branch, you can actually execute the x equals 1, fulfilling the promise, and there is no more need to certify again because there is no ongoing promises. And the execution is finished. So far so good. So this example is also explained with the mechanism of promise and certification because the promise and certification distinguishes is relied on semantic dependency instead of syntactic dependency, and it actually accounts for the compile optimization that is performed on the programming language concurrency semantics. Okay, so as I said, certifications and real execution may diverge to capture semantic dependency. Here is a bonus example where you're going to use see the need for a recertification. So this behavior is the left thread is the same, but in the right thread, R3 equals X is executed in between the first and the second instruction. So the behavior in question is that, is it possible to read R3 equals 1 as well, in addition to R1 equals R2 equals 1? In a sense, it should be forbidden because there should be RW coherence. This read and this write should be ordered, and as a result, this read cannot read from the later write. That's the reason why this behavior should be forbidden in the example. I mean, in the semantics. And let me explain how to forbid this behavior in the promising semantics. So in the same way, you may be able to promise to write x equals 1 in this example as well. Almost for the same reason. This is certified in the second example. And then the left thread may execute the two instructions, reading x equals 1 and writing y equals 1. And in the second example, in the second thread, you may execute you may read y equals 1 and x equals 1. However, after reading these two values, y equals 1 and x equals 1, and the view is updated to this point, you cannot recertify, because at this point of time, this value, this message here, cannot be fulfilled at all. Because your view is already here, then you cannot write to the message where you're already on here. Recall that you can only read and write on the area here, that is after your current view. It is on the current view that this cannot be fulfilled by the second thread in the promising semantics. And that's the reason why this behavior is forbidden. Or in other words, x equals 1 cannot be hoisted across this instruction, the reading from x, if this read need to read from the later store here. So that's basically the behavior in which recertification actually is necessary. Without recertification, you may have to allow this behavior, but it doesn't happen in the promising semantics because it requires recertification, and this recertification forbids the behavior in question here. Okay, let me summarize the technical content of the promising semantics. It is an operational semantics based on view and promises that is trying to model the relaxed behaviors and orderings. So there are 4 key ideas. One is multi-valued memory. It stores the entire history of the stores, and it is used to model the load hoisting. And there is the second idea is memory adjacency for modeling read modify writes such as fetch and add and compare and swap. And the third idea is views, which is modeling coherence and synchronization. And we also discuss such examples as coherence and the message passing, release acquire message passing, and fences. And also we saw the idea of promises, and this promises is used to model store hoisting. And the key idea was modeling the semantic true dependency using the idea of promises and certifications. And this is an informal homework, so that you don't need to submit to the GG. But please make sense of the examples in the promising semantics. Please understand why these behaviors are allowed and these behaviors are forbidden in the promising semantics. So there are many examples: message passing, load hoisting, store hoisting, as we discussed in the previous slides. And there are dozens of test cases in this link, Java causality test cases. And please make sure that those examples are making sense in the promising semantics. But except for those 3, because they are not correct or they differ from our understanding of the concurrency semantics. So only for the other examples, please make sure those examples in the promising semantics. Okay, so far we discussed the promising semantics, and it is going to be the end of this video. But I'd like to present one more slide on if you are interested in promising semantics. please go see such materials. So this is the paper that is presenting promising semantics, and there are also more low-level semantics for this promising semantics. So there are promising semantics for ARM and RISC-V architectures. So they share almost the same ideas, but they are tailored to ARM and RISC-V architecture, relaxed memory concurrency semantics, instead of C and C++ program language level concurrency semantics. We are also working on the x86 architecture's promising semantics, and it is going to be published probably this year or next year. And there is a program logic that is a formal reasoning principle for promising semantics, and there are a bunch of research ideas on top of this promising semantics. So we are almost finished working on promising semantics for persistent memory, which is a new emerging class of storage between the DRAM and SSD. So this is much faster than SSD, and performance is almost on par with the DRAM, but the data is not gone when the system is crashed. Even though the system is crashed, the value is still there in the persistent memory. But it may be casted that due to the cache coherence or some buffering, the value that is written in the program may not persist in the persistent memory. So we need to define a precise semantics for this persistent memory. In other words, which memory can be stored in the persistent memory when the system crashes. And we almost finished working on this promising semantics, and we are going to publish this year. And we can also think of a verified compilation for this promising semantics. Why we can verify or prove the correctness of compiler optimizations on top of this promising semantics, or we can model some ISA level concurrency features like interrupts or other kinds or cache manipulation operations, etc. So this is basically the research topic I am interested in on top of this promising semantics. And if you're interested, please refer to these papers or contact me on the future research.